Yeah.
So if you're given the concentration and also you know the molar mass, can you find that using molar, like to find molarity?
If I'm given the concentration, what is the concentration?
No, I'm just saying like in general, like one time on the test we were given the concentration and we knew the molar mass. And so I was thinking like you could do the concentration divided by molar mass to get the molarity.
Well, molarity is concentration. There's many ways to say concentration. You could do molarity, molality. Which concentration are you talking about?
I think the molality.
Yeah, if
That
you have the molality, you have the moles per kilogram solvent, right? So you have the moles. You're saying if they also gave you the molar mass?
yeah.
Yeah, if you had the molar mass, you could find the mass of this. Then you could find the percent by mass because you have the mass of the top and the mass of the bottom. You could add them up. You would be needed to get somehow to get the volume of this solution would be difficult. They would have to give you something to be able to give you the volume of it, and that would be like density if you wanted to go from this to molarity.
Oh, okay.
I have a question.
Yep.
So, when you did 100 grams times the 1 centimeter cubed over 1.11 grams,
Yes.
how did you go directly to liters and milliliters from the centimeter cubed?
1 centimeter cubed equals 1 milliliter.
Is it is that like a general rule or
That's yep. That's always. Yep. Sometimes in medical shows, you'll hear them say cc's. What they're saying is cubic centimeters. That's equal to a milliliter. The reason why they say cc is because doctors don't write very good. So they may see that as milliliter. In real terms, that could be microliter because that's the symbol for micro. If you got micro and milli confused, then you could end up killing a person. So they always use cubic centimeters, which is the same measurement. But they always say, give me 10 cc's this, right? You've heard it maybe in movies or maybe in real life. You've been through a lot of surgery. 2. Your knee from a skateboarding accident? No. Yes. 4, same page. 150 grams of sodium chloride completely dissolves in 1 kilogram of water at 25 degrees Celsius. The vapor pressure of pure water at this temperature is 23.8 torr. Determine the vapor pressure of the solution. So what we're going to need is the mole fraction because pressure final will equal the mole fraction of the solvent times the initial pressure. So to find the mole fraction of the solvent, we need moles of sodium chloride. What's the molar mass of that? 58.44. (150 divided by 58.44).
The answer is about 2.5667.
So 2.56 moles. So that's going to be on the bottom. Now the thing is that this is sodium chloride. So whenever sodium chloride dissociates, it makes 1 Na and 1 Cl. So the moles of particles down here will actually be multiplied by 2 there. Then we're going to add to that, we need to find the moles of the water. The moles of the water will go on top and there because it's moles of solvent over moles of all particles. That's what a mole fraction is. Moles of solvent over moles of all particles. That times 2 is because for 150 grams of NaCl, when it's dissolved, you get 2.56 moles of Na, and you get 2.56 moles of Cl, because it's an ionic compound. So 100 kilogram or 1 kilogram is 1,000 grams. Every 18.02 grams is 1 mole of water. 1,000 divided by 18.02.
It's about
55.49 moles. 2 times 2.567 plus 55.49.
That would be 60.624.
55.49 divided by 60.624.
It's about 0.9153.
And we're going to multiply that by this 23.8. 0.9153 times 23.8.
The answer is about 21.7841.
21.78, which is 21.84. Pretty significant. The key thing on that one that people don't do is they don't they don't multiply the moles of NaCl by 2, because you have moles of Na particles and moles of Cl particles. That is that I factor right there, that Van Hoff factor. You need to take and multiply that 2 by that. That is the I right there.
I have a question. I thought there wasn't an I in like the vapor pressure. I thought that was only in the osmotic pressure.
It is, but that's the thing. The I is actually in the in this X of the solvent.
Okay.
Yep.
So you multiply the mole fraction?
X of the solvent equals moles of the solvent over moles of the solute times I plus moles of the solvent. How's that?
So you don't multiply I times all of the solution, only the solute.
Only the solute, yep, because the solute's the only thing that breaks apart.
Okay, thank you.
You're welcome. How was lunch, Tegan? Is it Tegan or just Tegan? This is the first time you experienced it? Yeah. How's it varied since last week? Yeah. Is it like a McRib? No, I mean, I don't know. It's like Did hamburgers taste like meat? Whenever I was a kid, like the hamburgers, I think, were like soybean patties or something, and they never really tasted like meat. Yeah, right? Olivia, you want to throw another one in? Anybody else got a number at home? Peter, you got a number? $11 on page 24. What volume is needed to contain 3 moles of HCl? All right. So we want volume. How many units is that? 1. And we have moles or moles per liter. So which one do we want to start with? Which one has 1 unit? Moles or moles per liter? Moles. So we start 3.00 moles. Every 10.00 moles is 1 liter. Every 1 liter is 1,000 milliliters. 3 divided by 10 times 1,000.
It's 300.
3 divided by 10 times 1,000, 300. Looks like the answer key is wrong unless I messed up here. 3, 10 moles per liter, 10 molar solution. Every 1 liter is 1,000 milliliters. 300. What's up? Where would I need to convert it to grams? Is in moles per liter. Yep. That is specific to the HCl. Yep. That's how many moles of HCl there are per liter of solution. I wonder why that's off. It's only off by a decimal place, but yeah, right. Two on 25. How would you prepare 145 grams of an aqueous solution that is 2.5% by mass percent potassium iodide? 140 grams. All right, so we have 145 grams of total solution. And every 100 grams of solution has 2.5 grams of potassium iodide. 145 divided by 100 times 2.5.
It's 3.625.
So we have 3.3 significant digits, 3.63 grams of Ki. And then the total mass is going to be 145 grams, right? So if this is the mass of the Ki, how do I find the mass of the solvent? Subtract 145 minus 3.63.
It's 141.37.
So a lot of the questions tomorrow will be problems. And if you recall with these tests, it won't be multiple choice for those problems because that'll allow random generators to generate the numbers. So you'll need to write the answer in there, type the answer in there, just the number. Don't worry about unit. Those problems will probably be 4 points each. The other problems will be 3 points each, like, what is molarity, moles per liter, right? That's a 3-point problem. Between 30 and 25. Just like there are 1,000 millimeters in a meter, or 1,000 milliliters in a liter, there are 1,000 milligrams in a gram. Yeah, why did they even do that, right? That's pretty dumb. Others. Actually, there is this this is the solvent. They're both the solvent, actually. They're both dissolving each other. This would be a miscible thing. Actually, that's funny. This is the mole fraction of each component. Let's take a look. 35.45 times 4 plus 12.01. 35.45 times 4 plus 12.01.
That would be 153.81.
35.45 times 3. 45. Geez. 35.45 times 3 plus 1.01 plus 12.01.
It's 119.37.
50 divided by 153.81.
The answer is about 0.325.
50 divided by 119.37.
It's about 0.4188.
0.325 divided by 0.325, won't do that. 0.325 plus 0.419.
The answer is 0.744.
0.325 divided by 0.744.
It's about 0.4368.
Both of these are, they don't split. Yep. 0.419 divided by 0.744.
The answer is about 0.5631. Upper A, B, J, K, M, and lower E, J, L, N.
So remember that this is the individual divided by the total, individual divided by the total. This 0.744 came from me adding these up. I don't know why these don't match up, but that's close enough for me. I'm assuming it's probably because some change in molar mass, or I made a slight, whenever I added it up with the calculator, maybe I missed hydrogen or something weird. You only use the I value when you're dealing with colligative properties. Vapor pressure, melting point, freezing point, or osmotic pressure. Colligative properties. Yep. So if we take a look here, a non-volatile solute, basically something that's not going to vaporize, is added to a volatile solvent, something like water or gasoline or something like that, something that will vaporize, right? The solution vapor pressure, if we add this to it, the vapor pressure will go down. The boiling point will go up. The freezing point will go down. And the osmotic pressure will go up as well.
Could you explain what non-volatile and volatile
Yeah.
is again, please?
So salt doesn't vaporize, it just sits on the table, right?
Yeah.
Yeah. Water, we know will vaporize if let this sit there.
Okay, so it's whether or not they vaporize.
Yeah. You might have heard of a different definition of something like is volatile. A lot of times it's thought to explode, right?
Yeah.
Yeah, or if a person is volatile, their what do we think? Their attitude could possibly do what? Like they could explode. She's volatile. Have you ever called somebody volatile? But if we take a look, it's a substance that's easily evaporated at normal temperatures. I mean, water will evaporate. We said that if you had a dog pass away or a family pet pass away and you left the dish out there, then eventually that dish would be empty, even though the dog or whatever isn't there to drink it, right? Right. I just remember being a kid and that happening. And yeah, so it's always the example I get because I think it was probably my realization, as a kid, like, wait, why did this water go away if Puppy, I wasn't very good at naming things, so Puppy was its name. But yeah, right, if Puppy wasn't here to drink this, how did this water go away? And that, I think that led me to understand the idea, but yeah. So
Could we
salt
please
won't vaporize.
also,
It's non-volatile. Yep.
could
I'm
we
sorry.
please also go over like the vocabulary on page 21, please? I don't have like number 9 and number 12 across.
Description of how much solute is present in a solution. Can you give me a letter? Oh, that'd be concentration, probably. Will that fit? And what was the other one, number 12? A property that depends on the number of solute particles. That would be colligative. Colligative.
Sorry, could you say that again?
Colligative.
Okay, thank you.
Yep. Does concentration fit for this one? Is that what you got? Did you do that?
Yeah, it does.
Okay, cool. Which one? Well, what's the freezing point of water? What temperature does water freeze? Zero Celsius. So you subtract it from 0. And boiling, you add it to 100. To find the points, because boiling water boils at 100 degrees Celsius and water freezes at 0 degrees Celsius. Since it's water freezing point depression, we subtract from 0. Since it's boiling point elevation, we add to 100. So in your drawings, like whenever you draw somebody now, do you draw a lot of people or do you just draw? Yeah. Do you ever draw them with the mask on or do you?
No, not really.
It's kind of weird, right?
Yeah, it's like the most interesting part of it.
Yeah, right. Like the nose and the mouth and the difficulties of those, right?
Yeah.
But yeah, that's like, man, like maybe I could be a mask on artist because I'm not very good at those parts because they're the hardest part. Yeah, right. Just really good at drawing eyes. Yeah. And a mask and I'm done. Right. I wonder, like, there's like character artists and stuff. I wonder if they just sit there like, because they don't really know, right?
They don't have anything to get caught.
Maybe, yeah, right. Like you don't have a big nose or crooked teeth or what. It's like, yeah, right. Like, yeah. I'm just gonna put you riding one of those undersized tricycles or something. Of water, 1 gram is equal to 1 milliliter because that's the density of water. So it's freezing point depression. The freezing point goes lower than it's normally. So it's normally at 0. So it'll go down lower, right? If it's freezing point. And if it's boiling point, we go up. Because it's, yeah. This is why we put salt on the roads, right? In the wintertime. Because the freezing point of the water goes down. So it can be colder and the salt water will not freeze. That's the idea. Or if you've ever been, you probably haven't, but like, have you ever been to Kroger? Yeah. So they have like the wine section. they have this thing there where it's like this pool of salt water, and you can put your bottle of wine in there to chill it, so that whenever you take it home, it'll already be cold for dinner, right? So if you're going to pair up a wine with a dinner that you're making, but they use salt water there because it's much colder than regular water would be, right? Yep. Actually, did we watch last semester? Did we watch Killing a Beer and Killing a Six Pack? We didn't, did we? Yeah, there's a Mythbusters where they say, "What's the quickest way to chill a six pack?" And it's actually salt water and ice mixture. Everyone gets it cold yet? All right. Are there any other questions? Then I feel good. Do you? Any questions about the laboratory? You guys good on that? I mean, basically, I think that some people that had issues early on, they did not have concentration on the x-axis. And what that is that concentration is the independent variable. The independent variable always goes on the x-axis. That's why so often you see time on the x-axis, right? Because time doesn't care about anything. It just goes forward. It's not dependent on anything. It's the independent variable. For this concentration, the concentration is what determines the absorbance. So that's why we have concentration on here. For some reason, whenever I came in, I did not use the unknowns that I did last year, and that's why I was confused on Sunday whenever some people were reaching out to me. Last year, I used an unknown that was beyond 0.2. We didn't have that this year, as I saw whenever I got in. So they should have been all within your ability on that. For some reason, stuck in my head was that I was stuck on last year. I think that's the actual last lab we did last year. The timing's almost right, isn't it? Yeah, because we've been out for 1 year. That was the last lab we did. Yep. Yeah. 6 on what? 6 on 26. Describe how you would prepare an aqueous solution of 1.25. That's lowercase m, so that's not molarity, that's molality, right? Not a lot of this.
Can't see- You only see the Google sheet
Oh.
or
Yep, sorry.
page.
The Google page, thank you. So if we take a look, 1.25 moles per kilogram. They don't really tell us how much, so let's just take 1 kilogram of water. And we want to put 1.25 moles in there. But we can't measure moles in the laboratory. We don't have a molometer, right? A molometer. What would you say, molometer or molometer? Molometer sounds like fancy, right? Hand me the molometer. They don't exist, right? Because there's too many different chemicals. They don't exist. So we need to figure out every 1 mole of this substance, barium nitrate, has a mass of what? 137.33 plus 14.01 times 2 plus 6 times 16.
It's 261.35.
261, is that what you got? Yeah. And 261.35 times 1.25?
That would be 326.6875.
So we would take 327 grams of barium nitrate. And we would add that to 1 kilogram of H2O. What is the Van Hoff index for barium nitrate? I'm not. I'm just asking you. Nope, not 2. Not 1. It is 3. 1 mole of barium and 2 moles of nitrate for every 1 mole of barium nitrate. Others? The only way you can really get really good at these problems is through practice. So I do suggest that you practice one of each type at least. You could have. 1,000 grams and 1 kilogram is the same. Other questions? That's all I got then. If you do have a question and you just were shy, by all means, stick around, ask after the Zoom. Otherwise, I'm not gonna sit here and have you guys just stare at me in silence. So have a great day. Test tomorrow, no Zoom.